going into this tube, you would see a stream of light coming from the negative going toward the positive. And if you put that in like a magnetic field or an electric field, it would bend, which we'll get into later, but it bends it. And so they could tell which side it was coming from. Well, it was coming from the negative terminal, which, by the way, is called a cathode, C-A-T-H-O-D-E. Probably never saw it. There was a show on one of the stations, maybe 10 years ago, called Cash Cab. You'll ever see that show? You know, the guy would pick up people, and then they'd agree to work with him, and he would ask them questions, and if they answered them right, they got money. If they, missed too many, then sorry, set you out, you don't get any money. You lose everything. And I just remember one of the questions he asked was, this person was, what is the negative terminal of the battery called? They didn't ask it in that way, but that was the basic question. And the person couldn't think of the answer. And by the way, if you didn't know the answer, he would eventually give you what the answer was. So on the TV show, they're filming all of this inside his cab. Well, he said it was the anode. And I've always wanted to write in and tell him, you got that one wrong. The anode is the positive terminal. The cathode is the negative terminal. But anyway, I think the guy still wants some money, so that was okay. But this light, and what was happening was the electrons are coming off of that negative side of the battery, or what was hooked up to the negative side of the battery. And as they went through the gas that was inside the tube, they would collide with molecules or atoms in the gas, and they would cause then visible light to occur. Basically, electrons in the gas would jump to higher energy levels, fall back to the lower energy level, and the difference in the energy levels would be given off as a light wave, electromagnetic wave. But they could see that, and so they called them cathode rays. And since they were coming from the negative, well, it must be a negative charged particle. And then after other experimentation, they determined that they could get the charged mass ratio of those, and it was a very, very small ratio there. And so they could determine that eventually we renamed it, instead of cathode rays, they were called now electrons. Figure out they were particles, they were negatively charged. At least at that point, they could calculate, or they could figure out what the charge to over mass ratio of this particle was. And so we give it the name of the electron. But if you've got negative charges there, you also must have some positive charges. Because most things that we have experience with do not have a charge. They are neutrally charged. Well, but if everything's got these electrons, which they were able to easily show, if everything's got these negative charges, in order to be neutrally charged, there must also be the equal number of positive charges. Because your normal atom doesn't have a net charge, it's got a net charge of 0. So hydrogen has 1 proton and 1 electron. Okay, so it's got a +1 and a -1, and therefore the net is 0 charge. Helium has 2 protons and 2 electrons. Now, they didn't know all this at that instant, but as soon as they discovered the electron, but started discovering more about it. We know nowadays that we've got that. Uranium has 92 protons, 92 electrons, plus a bunch of neutrons. But most things are neutrally charged. They don't have more protons or neutrons or electrons. They've got the same number. So something is charged only if it's either got an extra electron ion. If you've got an extra electron on this atom, then you've got a negative ion. What is it? Sodium chloride, salt. You split the sodium atom and the chlorine atom apart. Sodium is a positive ion and chlorine is a negative ion. Because of the way the electrons go with them. But we give them now these names. And we say the electron is negative. That was what was discovered as the cathode rays. And then the proton is the positive charge. The amount of charge on each of these. Now we're going to use, and some equations it'll be capital Q and some little q. But Q, the charge, and with a subscript E, now you can think electron there, but it's the same charge on both the electron and the proton. So the amount of that basic unit charge turned out to be 1.6 times 10 to the negative 19. Units on that is a capital C, and that's the word Coulomb. French physicist that did a lot of work in the 1800s on electricity, trying to measure the force that one charge puts on another charge. That's the first big equation we got in this chapter. So it's named after him. Okay. That's the basic unit charge. Now, yeah, the 1.6 is ... after that. There's, I think they measured it down to at least 10 or 12 significant figures, something like that. We're just going to say 1.6, 10 to the negative 19. That's the charge on the proton or the electron. Positive is proton, negative is the electron. So, got that. As far as we can determine experimentally, or at least directly experimentally, that's the smallest charge that nature has. A guy named Millikan, back in the early 1900s, they knew the mass and the charge ratio for the electron and the proton, but they didn't know what the charge was, they didn't know what the mass was of either one of them. And he did this famous experiment called the oil drop experiment. Basically took oil and sprayed it into a small can, like container, to a container, and then he could look at it through basically like a microscope as these oil drops would fly in there. As they would be sprayed out into this container, well, the friction as they went out of the spray nozzle would create charges on the oil drops. And then the oil drop, there was air in the container, so the oil drop starts falling, gravity's pulling them down, but they'll reach a terminal velocity very quick. They're very small drops, and they're falling toward the bottom there. Knowing how fast they're falling, he could get he could do some calculations with some various equations from fluids and determine the mass of the oil drop. And so knowing that, he could get what the gravitational force was on them. But then he could also apply a voltage across the top and the bottom of this container. So if he's got an oil drop here, and let's say it's got a negative charge on it, well, gravity, mg, is pulling it downward. But if I put a positive charge up here and a negative charge down here, just like the Greeks found, if it's the same charge, there's a repulsive force. If it's opposite charge, there's an attractive force between them. So like the 2 pieces of amber, that was the same charge. They were both negatively charged. So they tried to repel each other. On the 2 pieces of glass, they'd strip some electrons off, so they were positively charged. They were repelling. But the piece of glass and the piece of amber were attracting each other because one was positive and one was negative. Same thing with electrons and protons. Or, so I've got too many protons up here, I've got too many electrons down here. Well, say the top and bottom plates here, they're hooked up to batteries to create this. And so there would be an electric force upward to try to attract it to the positive and repel it from the negative. Well, he didn't have real fine control on this charge that he could put on these, or the voltage across there. And so he couldn't get, if it had been real simple, if you could bring this to a stop, and then this force would equal this force, and it'd be real easy to determine what the charge on that oil drop was. Well, but he didn't have that good of control on it. And so he put a voltage across here, and if it was too big, then instead of falling, this would be rising. But if it wasn't big enough, this would fall, but it just wouldn't fall as fast. Because it had an electric force acting upward on it that either was more than the gravitational force or slightly less than the gravitational force. But he never did know, but he had to get it exactly balanced. So he could measure how fast it's falling with the electricity force acting on it. And then knowing that and how fast it was falling when it was just gravity acting on it, he could go through some calculations and determine what the charge on that oil drop was. Well, he does this thousands of times. You talk about a long experiment. He did this over and over and over, kept notebooks full of this data. And then when he started analyzing it, he noticed that, okay, you had, like, here's the charge, you had a bunch of charges down here at a certain amount. And then you had another whole bunch of charges at approximately twice that amount. And you had another group of charges at 3 times this amount. And this could be either positive or negative, by the way. Because the oil drop coming out could end up being negatively charged, could end up being positively charged. There's no way to tell. But he noticed that they were tended to be grouped. And this minimum amount of charge was approximately this 1.610 negative 19, or twice that, or 3 times that, or -1 of that, or -2 of that. And so he made the conclusion then that the basic charge was that amount. By the way, other people were also working on it at the same time. And actually, another experimenter did a better job than Millikan did. But I don't know, maybe Millikan published first or something. He got credit for it. Discovering the charge on the electron. Once they knew the charge on the electron, then they could also determine its mass. And since the proton was the same charge, to determine then the mass of the proton. So they were able to do that. And up until about 1960, everything was fine. But then in looking at nuclear physics, really, in particle accelerators, and they slam protons together and stuff like that to see what comes out, they came up with a new theory, and they said that, well, the proton itself is not a single particle, that it's composed of other particles that are even smaller than the proton. And he came up with the idea of what are now called quarks. The theory said that there ought to be 6 quarks. And depending on how these quarks combine, you get then other particles that we see experimentally. You get things like muons and K particles and all bunch of other names from the 50s, and really even before the 50s, up to that point. They kept doing all this atom smashing stuff, and they discovered that they kept discovering new particles, new particles, new particles. And they had like 100 of these particles. They said, they all can't be elementary particles, basic particles. And so how can we explain that they're not all basic particles? Well, they come up with this new theory now, which is now called the Standard Model of the atom. And it said that there are 6 of these quarks, and then there's also 6 very light particles, of which the electron is one of those. And so you got the 6 quarks, and they eventually ended up with names of up, down, really good names here. Strange, charm, top, and bottom. Those are the 6 heavy particles that make up everything else that we see. And then the light particles, these would be called, the basic name is hadrons, Greek name for heavy, and the leptons, the light particles, are the electron, and you've got the muon, which is about 200 times the mass of the electron. We've got what's called a tauon, T-A-U-O-N, yes, or maybe just T-A-O-N, I think it's T-A-O-N. And then you've also got the neutrino, but you've got an electron neutrino, a muon neutrino, and a tauon neutrino. And those then are the 6 light particles. And if you take combinations of all of this, then you can get all these other particles that they've been coming up with experimentally. Well, electron, is the 1.610 negative 19. Muon, tauon, I don't know what their charge is, but there's something, plus or minus one of those, that number. The neutrinos don't have a charge. They're neutrally charged. The proton is composed of 2 up quarks and 1 down quark. So this proton is, like you got 2 ups and 1 down that make up it. Then the neutron is 1 up and 2 down quarks. Well, according to the theory then, the quarks, they don't have the 1.610 negative 19. They have either plus or minus that, but it's plus or minus either a third of that or 2/3 of this. And I'm trying to remember, I think the up is plus 2/3 of this amount, and the down is negative 1/3 of that. Strange chart top and bottom, I don't remember. I'd have to go look it up myself at that point. It's been too long since I've even looked at it. But if you have 2 ups and 1 down, 2/3 minus 1/3 gives you plus 3/3, plus 1, which is the charge on the proton. And 1 up and 2 down, so plus 2/3 minus 1/3 minus 1/3 gives you 0 net charge. Okay. So that gives you the neutron. But experimentally, at least directly, the charge on the electron of the proton is still the smallest charge that you can observe directly. We know the quarks are there. The last one to be experimentally confirmed was about probably 15 to 17 years ago. I don't remember exactly when it was. Around 2000, maybe a year or two before 2000. I remember the big announcement coming out that they have confirmed that the bottom quark is there and all of that. But they know they're there, but you can't see them directly. You see them indirectly. So the theory said if you smash two protons together, you got these 4 ups and 2 downs that are flying around, that they will recombine in such a short amount of time that there's no way we can detect them as an individual particle. Even with all the fancy equipment they got, you can't, it's happening too quickly for you to detect. And then what comes out should be certain things. And if, the different quarks exist, the way the theory says they do, then you ought to see a certain percentage of this come out or a certain percentage of that come out at various angles with various energies. And so they do the experiments and they see all that happening. They confirm that yes, that is happening the way the theory predicts it does. And so we say, okay, well, yes, the quarks do exist. But you've never seen an individual quark, a single quark by itself. They always show up, and it turns out to be either in I think there's some particles, some of these exotic particles that can have 2 quarks, but most of the ones, or at least the ones that particles we normally see, are going to end up having 3 quarks combinations. And so, yeah, they're there, but you just can't observe them directly. These charges less than the 1.610 negative 19. So that's still basic. By the way, I'm not going to ask you any question on a test about quarks. But I like to throw it in. Plus, we need to at least mention a little bit about modern physics. Something past 1900. So we got protons, electrons, neutrons, basic charge, 1.610 negative 19 coulombs. Well, we say that if they're the same, it's a repulsive force. If they're the opposite charge, it's an attractive force. How much is the force? So Mr. Coulomb comes along. 1800s, he does the experiments, and he comes up with the charge, or the force that one charge puts on another, is the product of the charges and inversely proportional to the distance between the charges squared. And he measured that proportionality constant, which is now called Coulomb's constant. And that is approximately 9 times 10 to the 9. Just use that number. I'm saying 8.99 times 10 to the 9. Just use 9 10 to 9. And units would be Newton meter squared over Coulomb squared. So when you got coulombs times coulombs divided by meters squared, you end up with newtons for force. That's the force. That's the same kind of force that you have between 2 masses. That gravitational force between 2 masses. Remember Newton's big force equation was the big G constant times m1, m2 over r squared. Exactly the same type of force. Like Coulomb was expecting it to be that kind of a force when he did all of his experiments. But we have that. Now, in this equation, force, yes, is a vector. But for this equation, think of these charges as absolute values. So whether they're positive or negative, just put them in as a positive number. And what that gives you then is the magnitude of the force. Then you look to see what direction is it. Is it attractive or is it repulsive? Instead of trying to, I know there's a rule for determining whether it's attractive or repulsive, depending on the sign of the force. But don't worry about it. Just put them all in as negative, as positive numbers, get the magnitude, then look to see attractive or repulsive, trying to push it away or attract it toward the other one. So if you had two charges, let's say they're two positive charges, and let's say this is 5 microcoulombs, micro 10 negative 6, and this one is 3 microcoulombs, and they're separated by a distance of 1 meter. What would be the force that the first one puts on the second one? Charge 1 puts on charge 2. So I've got my 9, 10 to the 9. I've got 5 times 10 to the negative 6. 3 times 10 to the negative 6. Divided by 1 squared. And so I've got 45 times 3 is 135. And times 10 to the 12 negative 3, or 0.135 newtons would be the force. What direction is that force? Well, they're both positive charged, so it's a repulsive force, which means one is doing what? We're looking at the force acting on charge 2 due to charge 1. So that's going to be to the right. This would be what's called the radial force. It acts along the line connecting the two charges, parallel to that line. Well, that's repulsive, so it's trying to push charge 2 away from where charge 1 is. By the way, what would be the force? Say this is to the right. I don't know if you were calling to the right positive, you say that's positive that way. What would be the force that 2 puts on 1? Still all the same numbers, right? So it's still the 0.135 newtons. What direction is the force that 2 puts on 1? 2 is trying to push 1 away from it, so that would be to the left. But once you find one of them, you always go back to Newton's third law. For every action, there's an equal and opposite reaction. So if 1 is pushing 2 to the right, then 2 is pushing 1 to the left with the same magnitude. And now we're never going to get into actually probably asking that. It would just be, okay, what's the force that something puts on whatever? Only looking at one of those, you're not looking at all of them. Now, but remember, also, force is a vector. What if you've got more than one force acting on it? You've got more than 2 charges. What if you got a third charge? So what about over here? You've got a charge 3, and let's say this is positive, and that's going to be 6 microcoulombs, and the distance from 2 to 3 is 1 meter. What's the force that 3 puts on 2? I've got my 9, 10 to the 9, and the 6, 10 to the negative 6, and the 3, 10 to the negative 6, divided by the distance between them squared. And so that's going to be 9 times 6 is 54. 54 times 3, 150, 162. 10 negative 3 is 0.162 newtons. And which direction is it going to be? That's a positive, so that's going to be to the left. And so what is the net force acting on charge 2? So I've got this one to the right, I've got this one to the left, and they're in opposite directions, so I'm going to subtract them. So I could say to the right is positive, and the left is negative. And that would give us then a negative 0.0, what is that, 525 to 627 newtons, or 0.027 newtons to the left. That point depends on how you want to define directions. You want to use plus or minus, you want to use left, right, whatever. But they're in opposite directions. So if there's more than one force acting on a charge, you got to add all those forces together vectorially. Now, by the way, at this point, I'll make it a little easy on you. I won't give you forces that are not parallel to each other. Parallel in the same direction, you add them. Parallel in the opposite direction, you subtract them. But I could give you something like, here's my 5 microcoulomb, one. Here's my charge to 3 microcoulombs. And I'll put this charge 3, 6 microcoulombs. Put it on the corners of an equilateral triangle. Now what's the force that is total force acting on 2? Well, I've got force 1 puts on 2 going that way, and it's that magnitude, 0.03135. The force that 3 puts on 2 is still this magnitude, but it's not to the left, it's down. So it's something like that, where they're not parallel. Then you got to go back to adding vectors by breaking them into components and doing all that. Okay, this is x, this is y, that's 60 degrees, it's an equilateral triangle, so this is 60. And so my y component would be the F32 times the cosine of 60, and going this way would be the F32 times the sine of 60. And so my force in the x direction would be the 0.135 from the F12 plus the 0.162 times the sine of 60, since that's opposite that angle. In the y direction is at the 0.162 times the cosine of 60, but that's going down, so